Hey, hi everyone. Very good evening. Hi Chaitanya. Good evening. Hi Srisha. Hi Astosh. Hi Harsh. Great. So hope my voice is loud and clear there. Let's get into today's session. Before that, can you all do a quick recap? What are the topics we have covered yesterday? What are the topics that we have covered yesterday? Astosh, deep learning. Harsh, deep learning neural networks. Yes. Inside that, what are the things we discussed? Srisha, deep learning, artificial neural network, multi-layer neural network, single layer neural network, forward pass, backward propagations. Good points, Risha. And have you all gone through that backward propagation material, which is attached in your dashboard? Anybody worked on it with pen and paper, writing the derivations? But at least did you went back and try to understand how back propagation will work? All right, no one? Okay, Harsh is, yes, just took a glimpse. All right, Harsh, appreciate it. Others, I think you should have got what we discussed in yesterday's session itself. All right. So let's get into today's topic. Again, activation function, weights. Yes. So we discussed about optimizers, right? So why optimizers? Why we need optimizers? Why optimizers? Great, Sisha. To change weights and biases. Maybe you can find in your statement to get best weights and biases, we need optimizers. Okay. For control, for error control, yes, we can say that, Harsh, but the right definition it would be to get my weights and biases better. So for that, we need weights and biases. Sorry, optimizers. So what are the optimizers name that we have seen yesterday? What are the different optimizers available? What are the other optimizers available? Optimizers, different optimizers. Rushikesh mentioned one thing, gradient descent. I think nobody even gradient descent, right, Chaitanya? That's what one activate, so one optimizer we discussed yesterday. And there are different, why we need activation functions? Why we need activation functions? Is it to reduce error, Chaitanya? The control nodes. We can say which neuron need to be triggered, which neuron not to be triggered, and also to learn complexity from a data, because without activation function, it would be a linear equation. Right, Rishikesh, right. So without activation function, it will be a kind of linear equation. But to learn complexity of my data, to deal with images and videos, we are getting into non-linear activation functions. Right. So yesterday we discussed about the basic structure, what is the basic difference between deep learning and machine learning, and then the basic introduction part, how based on the biological neural network architecture, so how we are getting into this, how we are building artificial neural network, we learned it yesterday, and we built one network with multi-layer perceptron, and where we are having 3 layers: input layer, a hidden layer, and output layer. So we constructed it and we looked onto the mathematical equation, how it is getting done. Basically, this deep learning is nothing but a function of a function of a function. Why? Because you're having an input layer, output layer. So sorry, input layer, hidden layer, and output layer. So as I said before, I can have n number of hidden layers, right? So let's say the hidden layer, first hidden layer, you're taking h1. Let's take h1. H1 is equal to what? Activation function multiplied by one equation. So if it is going to the next layer, hidden layer, then what it will become, again, activation function. Now what it becomes, the previous layer h1 need to be connected to the next layer's h11 or something. So the whole network itself, we can say it's a function of a function of a function. So in this way, this network will keep moving. Able to understand this point, what I'm saying? All right, Harsh. Fine. So today's plan is nothing but, again, we are going to go study about the depth of optimizers. So again, it is going to be a bit painful to understand today, but anyway, we will give our best to understand this particular topics. I will be getting into the math part of all these optimizers, how it is getting done. The math it will be too much confusing, but I simplified it and I'm just trying to deliver it here. You just need to give your complete attention to this session, because again, it is going to be a foundation. So just try to give your complete attention in today's session, so that tomorrow once we get into the scripting part, you will be getting the complete stuff. Now today what we are going to discuss nothing but, there are different optimizers, different yes, Harsh, right. There are different optimizers, different activation functions, different loss functions. We have learned tested. Now, firstly, we are going to understand about what are all the different, we can say, different activation functions and the different optimizers what we have. And then we finally will be discussing about different loss functions. All right. Now, let us start with the very simplest one, that is different activation functions. See this. Let me share my screen. Yes. Let's take a look at it. Now here, firstly, we are going to understand about the different activation functions. Okay. So see this, here I'm having input layer, hidden layer, you can have hidden layer 2, hidden layer 3, anything, any number of hidden layers you can have, and here you're having output layer. Let's say this is an image classification problem for which you have to train your neural network. All right, give your complete attention. Now, here I'm having one particular image. Image is nothing but what? It is a combination of pixel values, right? So 0 to 255 we have. It's a combination of pixel values. Now what I'm doing, this all the pixel values, I'm just trying to send it to this input layer, and then it is just going into this and going into this all this network, each and every neuron. There is an interconnectivity between the previous layers neuron. All right. And finally, I would be having, let's say, if I'm keeping two neurons, one neuron is for Astosh and another neuron is for Nagarjun. Let's take it in this way. Now, if this neuron belongs to this Astosh, this neuron will be triggered. If this image belongs to Nagarjun, this neuron need to be triggered. Okay, that is the point ultimately. Now, I want to decide whether this neuron need to be triggered to the next layer or not, or this neuron need to be triggered, or this neuron need to be triggered. I want to decide it. For that, I'm just getting into this particular activation function. There are different activation functions available. I think yesterday I've shown you the different names. Now, the very first activation function, even what we had discussed yesterday, is something called sigmoid activation function. So the equation of sigmoid activation function, if you're taking it here, all right, H1 is equal to activation function. That H1. This H1 is equal to activation function multiplied by W1 x1 plus W2 x2 plus W3 x3 until it will go to W1 x1. So completely we can take it as what? F of x. Now, this f of x is equal to what I used to do. This where exactly this particular, if I'm keeping this particular activation function as sigmoid, 1 by 1 plus e to the power of minus y. So this is what the equation. Y is nothing but what? So whatever you're doing with respect to the calculation here, that value you have to subtract it over there. That's it. Now, what would be the output of this sigmoid? We know that sigmoid always ranges from 0 to 1. That's the range of sigmoid equation. Now, yesterday we learned about this major. Now, this is how the learning will happen. But the major problem of the sigmoid activation function, if I'm keeping the sigmoid activation function in my hidden layer, is nothing but, see this. Yesterday we learned this new weight is equal to old weight plus, it is not plus, it is minus basically. Sorry, that need to be corrected. Old weight minus learning rate multiplied by dou L divided by dou W old. So this equation is called as what? This equation is called as what? This equation is called as what? All right. Yes, Harsh, you are right. I think only Harsh is responding. Others just try to focus on the session and give you a response on the chat box. That should be better. So now see this. It's a gradient descent equation. Now, why we need to take gradient descent equation? Because I have to update the weights. In case if you're taking the sigmoid as one of the activation function in your hidden layers, what will happen? New weight is equal to old weight minus learning rate of dou L divided by dou W old. So old weight, let's say it is 0.05 plus learning rate, let's say I'm just going to give 0.5. And now this dou L divided by dou W, if you are keeping the activation function as sigmoid, because I'm back propagating. Whenever I'm back propagating, the activation function which is present in the hidden layers and also the output layer is pretty much important. Now, in case if you have kept sigmoid as an activation function in your hidden layers, what will happen is nothing but the total derivative, the total derivative value, dou L divided by dou old W, will be between 0 to 0.25. Okay, only this particular derivative value. If sigmoid is an activation function, the total derivative value will be 0 to 0.25. Now, if you're taking a learning rate, 0.5 multiplied by 0.25, now the previous weight is 0.05. Now, from the previous weight, when you're finally multiplying 0.5 multiplied by 0.25, now I'll be getting more number of 0. So here, the new weight is equal to 0.0025, which means that if this process keeps on going, my weight, it will be completely negligible. All right, because of the lower gradient values which I'm trying to get. So sigma, because of that reason, we call it as a vanishing gradient problem. This vanishing gradient problem is nothing but when I'm going for, let's say I'm just towards the right hand side, when I'm just going from right to left hand side, that is back propagating from the output node to the input node, it is again I need to go through a function of a function of a function of a function if the network is so deep. What do I mean by so deep? I will be having 10 hidden layers or 15 hidden layers. Let's say at the first hidden layer itself, I'm getting an output of 0.025. Now again, the previous layer, it will be very much reduced. So sigmoid activation function is not at all recommended to keep as an activation function in your hidden layers, but this sigmoid activation function can be kept in my output layer for binary classification problem statement, because the range, say output, the sigmoid ranges between 0 to 1, because if I'm keeping at the output layer, I'm not going to take the derivative of that. So the output of this is nothing but 0 to 1. Now, the final probability, if it is less than 0.5, I can say, hey, this class belongs to maybe Astosh. If the final probability, if it is greater than 0.5, I'd say it is, let's say, Nagarjuna or Prabhakaran, whatever the binary classification is. So that's what the point here also I just mentioned. If the final probability of this particular neuron, I'll keep only one neuron. Here I'll be getting one value, 0.567 or 0. So it won't go beyond 1. So 0 to 1, that would be the value. So if I'm keeping it, then it becomes a kind of probability equation or a binary classification equation, where if the final probability, if it is less than 0.05, sorry, less than 0.5, we can say this image this image belongs to Astosh. If the final probability, if it is greater than 0.5, this image belongs to Nagarjun. So this is what this particular point is. So sigmoid activation function is facing with the one problem called as vanishing gradient problem. Because of that, it's not really recommended to use sigmoid as an activation function in my hidden layers, but it can be kept for binary classification at your output node. Is this point clear? All right. So Harsh, Rishikesh, Supriya, Chaitanya, yes, sir. Fine. Now again, here the problem is nothing but again zero, the derivative value is between 0 to 25, 0.25 itself, but it's not increasing that much. So to overcome that particular problem, what I'm doing, I'm just, the researchers, they came up with another activation function. They called as tanh. We call it a hypertangent activation function, where it takes a mathematical equation f of x is equal to e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. So finally, the total derivative value, it will go till 1 for this particular tanh. In case if you're using as an activation function, it will go till 1, and it will go till 1, and the negative is nothing but minus 1. So the total derivative value, it will be between minus 1 to plus 1. So that's what this particular tanh is all about. So here, if you see, I'm just giving weightage to some negative pixels also, negative pixels and positive pixels. I'm just trying to include it. So tanh activation function, you can consider keeping in your hidden layers, not at your output layer, because it is minus 1 to plus 1. You can't take it for a binary classification problem statement. And also, we can't have negative values at the output layer, because it's going to be sales prediction or stock price prediction, or we can say weather forecasting. So in that way, we would be doing it. Now, reload, but the major problem is nothing but here, tanh is actually doing a pretty good job. But here, if you see the major problem, let's say here I'm able to have maybe let's say Rishikesh is here. Now Rishikesh wanted to go and hit gym, and he wanted to build up his muscles. Now Rishikesh, the day one, he's just trying to pick up 5 kg dumbbell, and he's able to lift it. He's able to do more reps. Now after 2 months, he's again doing it, and his bicep size is not at all getting increased. His total body is not at all getting optimized. Now what is happening is nothing but even though he's picking more weights, he's not at all, his weight is not getting optimized, or weight is getting increased. That's the point of this particular part. Now, when the weight, if it is coming, if the result, if it is more than plus 1, always it is going to cap to plus 1. If also it is having a lower cap also. If the lower weight, if it is more than minus 1.5, it is going to give a cap of minus 1. So always the output of this tanh activation function, so will range between minus 1 to plus 1. Now again, researchers were looking, this is not something efficient. Again, I want to come up with a new thing. That's when they came up with something called as ReLU. So where exactly f of x equal to. So for the positive weights if it is greater than 0, so they have given no restrictions. So whatever the value I'm getting it, the same value I will be using it as an activation function. But for all the negative weights if it is less than 0, I'm just making it as 0. So tan H activation function is really working good in today's market. So you can keep tan H or ReLU activation function in your hidden layer, but widely used is nothing but tan H. That's what we use it there. And the next activation function is nothing but leaky ReLU. Leaky ReLU is nothing but, if you see this particular ReLU part. So here for all the negative neurons, it is just I'm just trying to make it 0. But if that's the case, most of the neurons will become dead because it's a mathematical calculation which is happening inside. Most of the neurons will become dead. So to overcome that particular part, what I'm trying to do, I just wanted to slightly give some weightage to this particular negative pixels. So here what I'm doing, so here like the negative side, positive is nothing but same like ReLU because it's not a problem. But for when weights, if it is less than 0, so what I'm doing, I'm just trying to take one alpha term, alpha multiplied by x. So basically wx plus b plus w1x1 plus w2x2 plus w3x3. So in that way, plus b, finally you'll be getting one value. So 0.01 multiplied by that particular value if you do it. So because the weights, if it is less than 0, negative value, we can do the particular multiply by 0.01. So by doing this, I'm not completely eliminating this particular negative pixels, but I'm just capping between 0 to 1. In that way, I'm just capping between 0 to 0.5 something by multiplying with the constant 0.1, so that I don't want to delete some observations which is actually done in ReLU activation function. Are you all able to follow my point? Okay, great. Now see this. So in this way, we are having different activation functions. See this. Exponential linear. The next activation function is exponential linear unit. We call it EDL. So where exactly for positive weights, not a problem. But for negative side, I'm just taking exponential term, e to the power of x multiplied by 1 minus e to the power of x. In case if you're using exponential linear unit as an activation function, the values will be like this. Now, here if you see parametric ReLU is nothing but for here when weights, if it is greater than 0, I will be getting 0 to maximum value of this particular x. X is nothing but with whatever the input is coming in, I will be doing that. So when weights, if it is less than 0, then again I will be multiplying taking one constant called as alpha multiplied by x. So where exactly this alpha is here in parametric model, it is a parameter. So what is a parameter? It can be changed here. So now alpha, if it is alpha is equal to 0, if you just give alpha is equal to 0, then it becomes what? 0, right? So when weights, if it is less than 0, it is 0, which means that it is a ReLU activation function. Now when alpha, where exactly this particular, when alpha if it is equal to 0.01, where exactly we already discussed about it, we call it as light constant we are trying to multiply, we call it as a leaky ReLU. And when alpha if it is greater than 0 or greater than 0.01, we call it as something like a parametric ReLU because we are trying to pass out some values over there. Now the last activation function what we're going to discuss in the session is nothing but softmax activation function. Now if you see this particular softmax activation function, it is taking this particular equation e to the power of x1 divided by e to the power of x1 plus e to the power of x2 plus e to the power of x3. So in this way, this is what the mathematical equation. So softmax is used only at the output layer for multi-class classification problem. So you have the input layer, hidden layer, and the output layer. So when you go for multi-class classification, let's say whether you want to segregate between Harsh, I wanted to segregate between when this particular machine, if it is getting installed. So is it Harsh? Is it Chaitanya? Maybe is it Astosh? Is it Chaitanya? Is it Rushikesh? Now I just wanted to have a look at this particular inputs. All right, input accordingly I'll be creating it, but output each and if it is 4 outputs, I'll be creating 4 neurons. All right, each and every neuron speaks about one particular person. Now let's say I'm just trying to pass Nagarjun's image. So here at the output layer, all your data will be alphabetically ordered, and that particular name Nagarjun, is it in which label is it available? It is available in label 3. So this one will be triggered. and it will be showing into the picture. So now if you see 10%, 10%, 75%, and the last one is also 5%. The point is nothing but with respect to this, by using softmax activation function, I can go for multi-class classification also. So these are all the different activation functions that we have to know. And also there are other activation functions also, but now let me stop sharing my screen. I would be giving this material today. I think it's already uploaded again. So why we need activation functions? Because to trigger a neuron and also to learn complexity in my data. So we started by understanding sigma activation function, tan activation function, gradient ReLU activation function, leaky ReLU activation function, and we discussed about exponential linear unit, and we discussed about this particular softmax activation function, parametric ReLU function. So these are all the functions that we have discussed till now. So the major thing is nothing but Wx plus p, but before that, to learn complexity, activation function, and also it is going to say which neuron need to be triggered. Got it, everyone? All right, fine. Now see this. There are different loss functions we have. All right. But before this, if you look onto this, if you just go to this official website, maybe where it is. 1 minute. See this, get into Google and just type keras.io. Keras. So to work with this image related data or video related data, the very base library is nothing but Keras. Now there was another library called as TensorFlow. Now also it is available, but now TensorFlow, it's a very big library. To write the scripts with respect to TensorFlow, it will take a lot of time. But what researchers they came up and they have done is nothing but they taken this particular TensorFlow and they done a lot of modifications and they released the same thing with respect to something called as Keras. Now we can implement Python with Keras more easily. So if you to accomplish one particular task, if it is a TensorFlow old version, let's say 1.45 or 1.2, so you have to script it everything manually. But today's softwares and today this particular thing, how exactly it is working. So this working based on this particular thing. See this, once you visit this particular website, click on this get started. All right, click on get started. Just your website is the clue. All right. And here, if you scroll down, take a read on it later. Here we are having Keras API reference. Click on it. See this layer API, the layer activation. Let me click on it. We are having ReLU. So this ReLU activation function, what it will do, you can take a read here. What it will return sigma 1 by 1 plus e to the power of minus x. Softmax exponential of x divided by tf dot reduce sum multiplied by exponential of x. So soft plus this one mathematical equation. Soft sign this one mathematical equation. Tan h CLU scaled exponential linear unit. Even I have not used all the things, but here you're able to see what exactly fix if it is greater than 0, less than 0, what need to be done, what not need to be done. Everything has been clearly explained in this particular website. So keeping this website as a base, we will be working on our first project. All right, later you can take a read on this particular part. Able to understand everyone? Harsh, Supriya, wonderful. Great then. So before we get into this particular optimizes, so shall I continue or you need a break? Maybe 5 minutes. Shall I continue or you need a break before we get into optimizes? Are you all, is your mind good or you need a break? Yes, I wish. Okay, fine. Let's take maybe 3 to 4, maybe 4 minutes break. Let's take it. So again, because again, the next session, it's going to be a very long theory. It's going to be 30 minutes or 40 minutes theory. So let's take a break and then refresh your mind and then come back. We can get into it. All right. Let me start a 4 minutes timer. And post break, we will come back. We will learn about different optimizers. And then we can wind up our session. Okay. 4 minutes time. Hi everyone, it's all back from break. Fine. So now let's get into this topic. Main topic, it is optimizers. It's going to be a bit hectic to take it, but let's start it. So now why we need to learn about this particular optimizers, nothing but, so to achieve optimize is all about to achieve something towards the best, we call it as one. Is there any background noise from my side or is it okay? Is there any background noise or is it fine? Okay, fine. So let's continue this. So why this particular getting some disturbance? I think it shouldn't be. So now why this particular different optimizers, nothing but see this, my network need to learn better, because even whenever we are going and hitting gym, let's say we wanted to optimize ourselves. So let it be weight gain or let it be weight loss, optimizing. Hey, I want to reduce my weight. Why? Because we have to look better. Hey, I want to put some weights and I have to show some muscles. I need some muscle. Why? Because we have to optimize ourselves. Why we are learning data science and wanted to get into this data scientist job role? Because we have to optimize our job profiles. So why we have to write a book and publish it on Amazon? Because we have to optimize our features, whatever we are learning. So optimization is nothing but to achieve something towards the best, we can say in simple terms, it's an optimizers. Now here we are having a neural network which need to be optimized. So what do we mean by optimizers? The law, we are getting a loss and that loss need to be equal to 0. I want that to happen. So for that, we are jumping into optimizers. So what are all the different optimizers we have? Let's start from here. Let me share this screen. So all these materials I've just already given. So let me start from this particular point. See this. So optimizers are algorithms or methods used to change the attributes of your neural network, such as weights and learning rate, in order to reduce the losses. Optimizers helps to get results faster, because how quick we are able to achieve data scientist, how quickly we are able to achieve something faster. Hey, I want to reduce my weight. How fast? So time is also very much important. So there are various methods, or we can say there are different types of optimizers we have. One is gradient descent optimizer. Second one is stochastic gradient descent optimizer, mini batch gradient descent, stochastic gradient descent with momentum, NAG optimizer, ADA grad, RMS prob, ADA delta, ADAM optimizer. So these are all the various methods of optimizers. Now, before we get into the next slide, so there are few terminologies which we have to be aware of. First is nothing but epoch. Epoch is nothing but the number of times the algorithm. It's nothing but iterations, we have already learned it. Sample is nothing but we can say is a single row or single observation. Batch is nothing but it denotes the number of samples to be taken for updating the model parameters. Learning rate, we know that it is a parameter that provides the model a scale of how much model weight should be updated. Cost function and loss functions, they both are same. It is nothing but the loss function. Weights and biases, these are all weights and biases we call it the learnable parameters. The other term of weights and biases, learnable parameters in the model. Right. So once we are good with that, now let's go to this particular idea behind gradient descent. See this. So all this theoretical material I'm just giving it to you, so that later when you're facing any sort of doubts or something, you can come back and read this particular long theory. This I made it in Excel sheets. Now I just collected it and I've just presented in this PowerPoint presentation. Later you can come back and you can take a read on it. Now if you see see this. So almost all optimizers in deep learning is based on gradient descent. All right. Consider you're holding, yesterday I think I've mentioned the same thing. Idea behind gradient. Consider you're holding a ball resting at the top of the ball. When you lose the ball, it goes along the steepest direction and eventually settles at the bottom of the ball. So a gradient provides the ball in the steepest direction to reach the local minima, that is the ball of the bottom of the ball. So when I'm releasing the ball from the top of the ball, it need to reach the bottom of the ball. So the weights are, so in order to move from one point to the another point, it needs some push. So that's what we call it as a gradient over here. Now, there are three types of gradient descent. One is batch gradient descent, second one is stochastic gradient descent, and the third one is mini batch gradient descent. All right, mini batch gradient descent. Now, what is this particular gradient descent? Is nothing but, see this. Now, let me just come back here to the first slide. Let's understand from that particular point. Optimizes. Yep. See this. Gradient descent optimizer. So this is what the point what I was saying. So here you can just think of it. All right. So this kind of line, if I'm just dropping a ball, if you see this kind of graph, if I'm looking onto it, you can say it's a parabolic graph, because y is equal to f of x. F of x is equal to, I'm just giving x square. So just a kind of parabolic, because we know neural network itself, a function of a function of a function, we can say. So this point we are calling it as a local minima point, or we can say global minima point. There is a difference between local minima and global minima. Here, local minima and global minima, note down this particular terms, very much important. For this kind of behavior, we call it as a convex curve. So for this kind of behavior, if this is the type of the network, we call it as a local minima. So now when weights, if it is increasing or my increasing or decreasing with respect to the weights, my loss function need to be reduced. This is a two-dimensional graph. In case if you wanted to see in a three-dimensional graph, see this. Now I'm just projecting this particular y-axis as a cost function, weights and biases, I'm just taking it. So since I'm projecting in the three dimension, it will be looking like this. All right, where exactly this is the point where I wanted to reach. Maybe I would be from here, I will just go down and I wanted to reach it over here. Now this graph, if I'm just representing in a 2D projection, so this graph we call it as a contour graph. Okay, just for a theoretical understanding, we made it. So 2D projection of a 3D surface, we call it as a contour graph. Top view of 3D surface. Now, if you're looking onto this particular 3D surface from the top, it would look like this contour graph, right? Now, we know that the weight updation equation is given by new weight is equal to old weight minus learning rate of dou L divided by dou W with respect to old weight. How much old weight I have to tween, we can say tweaked or tune, so that we will be getting a new weight. The similar way bias also need to be tweaked. All right, learning rate, see this, where exactly alpha is nothing but learning rate, which determines how fast or slow it need to converge. All right, now how exactly this was going to happen? Now see this, let's take for example, you're having 100,000 images. This is all about how exactly gradient descent is working. I'm trying to explain it. You're having 100,000 images in your hand, or what we can say, it is a 1 million images you're having it. Now you're having input layer, n number of hidden layers you can have, and you're having output layer. Now what need to happen is nothing but when you're providing your gradient descent is all about whole data, your 1 million data, you have to take it at once. You have to send it to the feed forward neural network. This neural network, we also call it as a feed forward neural network. Note it down, FFNN, feed forward neural network. Now, when you're taking this 100K images at the time and sending it to this particular neural network for learning, it need to calculate the loss and it need to come back. But the major point itself, let's take, for example, 100,000 images. Now, let's imagine your each and every image is 1,000 by 1,000 pixels, because image is nothing but what it deals with the pixel values, right? So the length of each and every length and width of each and every pixel image is nothing but 1,000 by 1,000. Now, if you calculate it, it is 10 to the power 11, 100 gigabytes. Now, to process 100 gigabytes at one shot, do we have the RAM memory with our GPU in our machine? 100 GB we need it. We don't have it. So when you're trying to take all your images like this, when you're having more number of images, when you wanted to take it at once, you can rely on gradient descent, but the problem is it is going to do or throw you an error called as out of memory problem. So your gradient descent it will work better, but the problem is when you're trying to take all your data sets together to forward pass and backward pass, if it is happening, so it needs some storage memory to store all this weights and biases and backward parts and again new weights and again. So I need more processing power or more load to do this operation. when if I'm not having this gradient descent is not the right option. So what will happen is nothing but, so gradient descent is actually a good process, but the point is, so the point is, see this, I would be here, I would be here. So now I'll need to slowly come down and I need to reach this particular point. Or at this point we call this a global minima. So your gradient descent will come and reach, but in case of the data set load, if it is pretty huge, it will never reach it, because here itself it is going to say out of memory problem. In case if it is, if the data set size, if it is small, then you can rely on this, it is going to reach like this. Okay. Now let's imagine you are having 100,000 image in your hand. Let's take it in this way. Now, with gradient descent, the way of learning itself, I wanted to do. So what I'm doing is nothing but I'm just dividing this 100,000, 100K into multiple batches. Multiple batches, nothing but multiple portions. Now what I'm doing, this 100,000 images, I'm just dividing into, divided by 10. All right, let's say, or maybe 100. Let's say 100 mini batches, I'm just doing it. Now what will happen? 1, 2, 3, 4, 5, 6, 7. All right, so this will be like 100 images, 100 images, 100 images, 100 images, 100. This is nothing but one batch, we can say. All right. In this way, I'll be having 100 mini batches. All right. I will be having 100 mini batches. So for one iteration, that is one epoch, how many times I have to go for forward pass and backward pass is equal to how many mini batches? 100 mini batches. So 100 forward pass and 100 backward pass is equal to one iteration. Now what will happen for one iteration is equal to, this is going to take this particular first observation, this 100 images, 100 sets, 100 images at once. It is going to feed forward to the neural network. I'll calculate the loss. All right. I come back and I update the parameters. Now I take the second set of 100 images. Now with the updated parameters, I'm just coming back. And again, I'm just going to calculate the loss, go back and update the weights. Now third set of this particular parts. Now again, I'm going back. In this way, I'll be doing it. So because of this particular part, we are overcoming this particular out of memory problem. But the point is, the shortest way is nothing but reach like this. But here what it will do, because of you're taking batches by batches, it will travel like this kind of zigzag curve, lot of vertical curve, and finally it is going to reach it. We call this particular process as mini batch gradient descent. Instead of directly passing your complete data at once, so you're trying to take data like batch by batches, and you're trying to send it to the network for better learning. But here there is a problem. It is nothing but it is taking a lot of vertical movements instead of directly reaching to this particular global minimum point. So again, what they are doing, is there any other way? Fastly have to converge, is there any other way? That's when they came up with something called as stochastic gradient descent. Stochastic gradient is nothing but, here I'm from, let's say 100,000 images, I'm having it. Now stochastic gradient descent, what it will do, instead of instead of dividing it by 100 batches, I would be sending only one image. All right, only one. I'll take one image at once, send it to the feed forward network, calculate the loss, update the parameters. Second image, send it, calculate the loss, update the parameters. Third image. So because of this, we're taking the image one by one. Again, it will do a lot of zigzagness. And finally, it may reach or it may not reach the global minima, because every time it is going to see a new set of images, maybe it will get confused. So with respect to gradient descent approach, these are all the problems that I'm trying to face. A simple gradient descent, it is fine, but the major problem is nothing but, in case if you're having more data set, so the load it is not going to take it. It is going to give you an error like out of memory problem. To overcome that, mini batch gradient descent is better compared to gradient descent in times of, we can say, in lines of speed, we can say, because it is trying to take overcome this particular out of memory problem. Stochastic gradient descent, it is also we can say faster compared to many batches, because one image processing it and coming back, one image, but the time is nothing but, again, it is going to travel lot of zigzagness. So out of all this three things, mini batch is comparatively okay, comparatively performing good other than others. Able to understand what I'm saying? Yes or no? Let's confirm everyone. Now the same point here I just mentioned, you can take a read on it later. This batch gradient descent, that is nothing but your normal gradient descent. We also call it as batch gradient descent. How exactly it is happening, entire data set, and you can just read it. All right. See, this gradient descent works well for convex functions, but it doesn't know how far to travel along the gradient for non-convex functions. We will be knowing this particular part in a while. The benefit is nothing but the gradient path will be smoother. Now, again, stochastic gradient descent is nothing but what? Randomness. So a single sample is randomly picked up. You can just take a read on it. So you can, why stochastic over gradient descent? I've just given some points. The drawback of stochastic gradient descent, that is nothing but picking one observation at once. It's nothing but full of noise. It needs higher number of iterations to reach global minimum point. So, and again, mini batch gradient descent. Why mini batch gradient descent over normal batch gradient descent and stochastic? I just listed on few points. And drawback is nothing but maybe the batch size we have to mention manually, but that's comparatively okay. That's what I should say. So how do you choose between this? I also given some points. We can take a read on it later. Right. Now, the point here I just mentioned is nothing but all your gradient descent related methods. It is going to perform well if it is a convex functions. Now, what is the difference between convex and non-convex functions? We need to understand. All right. So now what we can do, let me go back here. All right. See this, I think here I've not given, but let us understand from this particular Google convex and non-convex cost function. Yep. Now see this, maybe we can take it in this way. This is my convex function. This is my non-convex function. Basically, we do not know how exactly whether it is a convex function or non-convex function, but based on some factors, how exactly the numbers are, we can come to know it. Maybe all these numbers and everything you might not be understanding it now, but tomorrow once we get into the scripting part, you will be knowing what exactly I'm speaking. But just load it in your mind now. See this. This is how it is just trying to learn. All right, convex function. Now, if the path, if it is very smoother, achieving the loss function is pretty much easier. But now for non-convex functions, it will be like this. So this blue color point is nothing but we call this a local minima point. And this blue color point, we call it as a global minima point. Now, if I'm using this gradient descent, what exactly gradient descent will think is nothing but my local minima is my global minima. All right, as I said before, there is a difference between local minima and global minima. Your gradient descent will work only for convex functions. It will never work for non-convex functions. So it will think that my local minima is my global minima. Local minima is nothing but, actually it is the lowest point, but again, we have to travel back. We have to go for another steepest, to travel for some more steepest direction, and then we have to come down. It's like of climbing a mountain. All right, there will be a peak and down, steep and everything. Finally, you have to go down. That's what the point. So when you're going down again, you have to climb back, right? So that's what the point is. So it was unable to push from this particular local minima. It needs a push. So to give a push, we need a person. Let's say whenever I used to say this, whenever you're learning this data science or machine learning or what the contents, so most of the times you will feel frustrated because this path demands a lot of time, a lot of patience you need it. Slowly you have to study, and because of that, you will lose motivation to study. Someone need to push you. Hey, yeah, you're doing good. So definitely you will be getting it. We need some motivation, maybe self-motivation, or we even we listen to some videos so that we can get motivated by ourselves. So that kind of motivation we need to have, so that we will push ourselves from this particular position and we can reach where exactly we wanted to. So to give that push, we are getting into the next optimizer. We call it as momentum optimizer. All right. So we call it a stochastic gradient descent with momentum optimizer. Now see this. If we can call momentum or stochastic gradient descent with momentum. Why this particular term? Again, now you'll be understanding in a while. Now, see this normal gradient descent weight updation equation is given by, let me zoom in. New weight is equal to old weight minus alpha t. learning rate dou L divided by dou W, old weight. Bias is equal to new bias, because new bias and weights and bias together, it need to be optimized, right? Bias old minus learning rate dou L divided by dou B multiplied by B, bias old. Now, instead of these two divisions, all right, dou L divided by dou W, only these two parts is getting divided. It is getting replaced with something called as VDW, and here it is getting replaced by VDB. Now, this VDW we call this exponential weighting by exponential weighted moving average methods. Very important. Now, what is this exponential weighted moving average methods? This VDW is given by beta multiplied by VDW t minus 1 plus 1 minus beta dou L divided by dou WT. And in the similar way, bias also. Now, what is this particular VT? That is averaged at time t, and VT minus 1 is nothing but average time till till previous time, and theta 1 is nothing but new weight. So by using this exponential weighted moving average method, my momentum is going to give a push. Push is nothing but I have to forget the old things and give more priority to the new things. So look onto this mathematical equation, how beautiful it is. Give your attention here. Now see this. This is BT is equal to beta is nothing but a constant. So this beta is not a constant, is a parameter. Basically, we can give anything. So here it would range between 0 to 1. All right. So what I'm doing, beta multiplied by VT minus 1 plus 1 minus beta multiplied by theta t. Theta t is nothing but a new weight. All right. Now see this. Now look onto this very carefully. Now you're having some data set in your hand. All right. Now let's say we at time t, all right, because at time t is nothing but 0th time, we are having the whole equation become 0. Now V1 is equal to what? Beta, let me zoom in, beta multiplied by t minus, now if I'm at time 1, the previous time is V0 plus 1 minus beta multiplied by theta 1. Or theta 1 is nothing but the new point. Now this V0, this part equal to 0, so 1 minus beta multiplied by theta 1. That will be the resultant here. Now the next time Bt is equal to beta multiplied by V1 plus 1 minus beta multiplied by theta 2, new incoming point. Now if you see this beta multiplied by V1 is nothing but what? 1 minus beta theta 1. I'm substituting it here, 1 minus beta theta 1 plus 1 minus beta theta 2. So both this equation, both the sides is having 1 minus beta as common. So I'm taking 1 minus beta, and beta theta 1 I'm taking it, and then theta 2 I'm mentioning it here. Now again, what I'm doing, 1 minus beta, I'm just rearranging it slightly, theta 2 plus beta theta 1. Okay, right. Now V3 is equal to what? Beta multiplied by V2 plus 1 minus beta multiplied by theta 3. That is the new weight. Now here if you see, beta, V2 is nothing but 1 minus beta theta 2 plus beta theta 1. Already I substituted. And 1 minus beta, I'm having it. Now again, with respect to these two equations, 1 minus b is common, I'm taking it. Now again, I'm just taking this theta 3 plus beta theta 2 plus beta square, right? Sorry, beta, 3 beta we have. Beta square theta 1. Because 1 minus beta I've already taken as a common here. Now the next point, at the next time interval, exponential weighted moving average, when I'm just moving forward with respect to time. All right. Let's say you are going with one speed, you're riding a bike. So how exactly you will move with respect to time, that's what in that way you can think of it. So at time 4, beta multiplied by V3 plus 1 minus beta theta 4, beta multiplied by V3 is nothing but this equation. I'm substituting it here, plus 1 minus beta theta 4. Now again, I'm just taking 1 minus beta common here, taking out. So again, I'm just arranging it like theta 4, beta theta 3, beta square theta 2, beta cube theta 3. Now, if you're looking onto this particular part, so in case if I'm substituting beta is nothing but 0.9, beta value will be mostly 0.9. If I'm substituting it, so when I'm just forward propagating in time, so here the third point will take 0.9. And the next point, and one step previous to that point, 0.81. And here beta cube, it will be reducing. So I will be giving more weightage to the newer points, and the weightage will be reduced to the older points. So now what will happen? Now I'm not going to carry the older weights. I'm going to give more weights to the newer points so that it is going to give a push, and it is going to move from the local minima to the newer, to the global minimum point. So by giving a push like this momentum, I'm able to overcome that particular, I'm just overcoming the trap of local minimum point, because weightage 0.9 weightage I'm going to give to the current point. So current point and the previous, sorry, this point is a new point, but once the previous to that point, I'm just giving a push. Hey, you need to go with 0.99. So this push you wanted. So because of that, it is just going traveling from this, and also a bit less weight compared to the second point. Also, it is just taking some weight over here, because if you see, with respect to this equation, I'm already having learning rate, and also I'm having beta. So learning rate is some one parameter, and also I'm introducing another parameter called as beta, which is nothing but a momentum. So learning rate is also happening, a push is also happening. So now I'm able to overcome this trap of local minimum point. So with a great push, it is going to push itself, and it is going to travel from local minima to the global minimum point. Able to understand this? Momentum. That is a math with respect to momentum optimizer. Able to get it, everyone? Just let me know. Again, there is a lot of math, other maths which is available. I'm not expecting 100% understanding here, but if you're getting slight picture, that should be fine. Supriya, Rishikesh, fine. All right, let's move further. This is what we called as a momentum optimizer. Now the next optimizer is nothing but wonderful. The next optimizer is nothing but it is a NAG optimizer. So here, if you see, yeah, see this. Here I just given whatever the points I just mentioned, I've just given it. So you can take a read on it. Stochastic gradient descent is much more noisier. So why stochastic SGD with momentum over normal SGD? Because of that, because faster convergence of the loss function. You can take a read on it. So, and also let me show you another thing, why momentum works better. If you see this, if you look onto it, see this. All right. Now let's say here I'm having Astosh is here. Now let's say Astosh is at this particular starting position. Now he wanted to become a data scientist. All right. Now what he is doing, he's just studying. He's just slowly studying. I'm just slowly, see this learning rate, it is just getting increased. Now I'm slowly studying the things. I'm just with the pace and I'm just studying it. But whatever I've studied initially, I'm just forgetting it. All right. And I keep on studying. I just wanted to reach it and keep on studying it. Only the learning rate, increasing the learning rate fastly. I'm just studying it. All the initial topics, my mind is not at all accepting, and I'm just increasing the learning pace. Finally, I'm lost. All right. I was able to reach this particular position, but this is where a data scientist I can do. So this distance, I'm not able to reach it. So only with the learning rate, I'm not able to reach my destination. We were in normal time, in normal words, we can take it in this way. I'm just keep on studying for a longer period of time. I'm not at all getting placed. I'm keep on, how long are we going to study? We have to get placed or we have to reach our destination. That's what the point here. So during our path, see this, only with learning rate, we are getting lost. So now what I'm doing, so with this particular learning rate, when I'm just having this kind of, when I'm just forgetting this new topic or when I'm not getting it, slowly I'm just, there is a mentor or there is someone who will motivate you, and I'm just going to give this kind of momentum. Now you're going to, now your path is a little bit smoother towards reaching it, towards reaching it. Again, you're learning it. Keep on learning it. And again, there is a smoother path, which I'm trying to get. All right, now you reached it. All right, maybe this, let me reduce, increase it. Anyway, you see, now I anyway reduced. Now I reached it, right? I reached it. There's something fine for me. So this is something nothing but whenever I used to hear this from my learners, sir, whatever the topics I learned it in the previous session or the first session, I forget it. That's something obvious because human brain will work in that particular way. If I'm asking some questions which you have studied in your first year college, you won't be able to answer well unless and until you are a faculty or a trainer like me, because we used to deliver the contents for multiple batches, same contents again. If you are not doing that, even I used to forget the things. If I'm just giving a gap of 2 years or 3 years, I forget it because human brain, in that particular period of time, it might have done a lot of other steps. That's what our human brain will remember. So the initial topics it will be forgotten, but that's fine. So, but here I just reached it. So the process nothing but learning rate alone, it will never work. Some motivation also we need to have it. From the local minimum point, I have to push myself to reach the global minimum point. For that, I need some momentum. So for that reason, we are getting into this momentum optimizer. Now, able to get it? Why momentum? Supriya, Harsh. Fine. Great, everyone. So now let's go further. Now the next optimizer is nothing but NAG optimizer. NAG optimizer, what it will do, see this. I'm not getting into the math of NAG, but just you can have an idea. NAG optimizer is nothing but it is slow down the speed when it reaches the local minimum. This method is also called as look ahead method. The point is nothing but you can just think of it. When you're climbing a mountain with respect to car or a bike, when you're taking it, when you're seeing a hairpin bend, your eyes is already has seen before. So looking ahead, so automatically will reduce the speed. So only with momentum optimizer, what it is happening sometimes, it is crossing beyond the global minimum itself. So to reduce the speed of this particular globe of this particular network or the model, when it is trying to reach towards the global minimum, it need to reduce the space. The speed it need to reduce it. For that, I'm just getting into Nestrov accelerated gradient. See this? Mm, mm, all optimizers, if I'm checking for it. Maybe this one. All right. Just take a look at it. This is my red color. See this stochastic gradient descent it is. So how smooth it is. This normal gradient descent one. All right. Normal gradient descent. How smooth it is, but it is taking a lot of time. Out of memory problem. It might not able to reach this global minimum. But if you see this green color momentum, how fast it is traveling. Look onto it. It is just coming and hitting here, and it's just traveling it. But this is where exactly I have to stop. But if you see green color, it is going beyond it. So to reduce this particular velocity, I'm just getting into NAG optimizer. See this, when I'm reducing it, when I'm reaching it, I'm slowing down the speed. So NAG optimizer, this is how this particular NAG optimizer is working. Call it again, it is having its own mathematical equation, a lot of equations there, but we are not anyway practically we are not going to write any mathematical equations in our work profile. So but you can just take a read on it, how exactly look ahead is working with another mathematical equation. You can take a look on it, but let's try to get into the other optimizers, which is pretty much important. So see this snag optimizer, I think you got an idea. Now let's move on to the next optimizer, that is ADAGRAD. All right, ADAGRAD. So ADAGRAD is nothing but very important thing. So one disadvantages of all optimizers explained is that the learning rate is constant for all parameters for each cycle, right? So learning rate 0.5, 0.4, something we fixed it. But here with respect to ADAGRAD, the name itself says adaptive gradient optimizer. So the need of dynamic is nothing. See this. Here, so the few points. This optimizer changes the learning rate for each iteration with respect to time. Whenever let's take for example humans. Now today we are learning this optimizer. We are trying to give our best, focusing on the session very slowly. We are trying to take it. Now after you have learned a lot of things. Now tomorrow is your examination. Will your learning pace will be like this, going very slowly? What do you say? Will he give this much time, 2 hours time only for optimizers? What do you say, everyone? No. So my learning pace is not going to be like this, right, Srisha and Harsh? So I will be going very fast. So my learning rate need to change with respect to time. Adaptiveness, it need to be there. So this optimizer changes the learning rate eta for each iteration t. We don't need to manually tune the learning rate for each iteration. So able to train on sparse data. We can look onto it later. So with respect to this mathematical equation, it is able to do that. You can take a read on this particular part later. Now let's go back to this blackboard. Let's understand how adaptively it is trying to learn. Let's try to understand that. Yes, ADA-grad. Again, see this another mathematical equation. Now take the base as your normal gradient descent equation. New weight is equal to old weight minus learning rate, dou L divided by dou W old. So this is what your here learning rate is constant, right? With respect to your normal gradient descent, momentum and everything. Even NAG also it's something the same. It's exactly the same. Now ADA-grad, here they're introducing something called as adaptive learning rate. See this, again a mathematical equation. Now instead of this particular thing, here I'm just giving eta dash. Eta dash nothing but the current learning rate, okay? And dou L divided by dou W. So this eta dash is given by eta divided by square root of alpha t plus epsilon. Now this eta, which I'm just giving in the numerator, is nothing but initial learning rate. Initial learning rate need to be fixed by some value, 0.00, 0. Some value need to be fixed. So let's say eta is nothing but 0.01. Okay, the initial learning rate is 0.001. Let's try to fix it. Divided by square root of alpha t. Now what is alpha t? Where alpha t is nothing but sum of squared gradients. That is alpha t is equal to summation of dou L divided by dou W I the whole square, sum of squared gradients. Now what will happen after several iterations? Let's say you're going with the iteration 1. Okay, so this one is nothing but what? Dou L divided by dou W. If you're doing it, you'll be getting a value of 0.5. Let's say you're getting a value of 0.5. Summation plus, and again another value, 0.05 plus 0.05 plus 0.05. So finally, this total value, it will be very higher, right? When the number of iterations, if it is increasing, this alpha t, it will be very higher. Now, this higher value, if you are just taking a square root, and if the total denominator, it will be a very higher value. Now, when the very smaller value like 0.01 divided by this particular very higher value, if it is happening from 0.001, it will be even more reduced. Are you getting my point, everyone? Yes or no? Are you getting my point? After multiple iterations, my alpha t will keep accumulating its result, and finally here I'll be getting a higher value. Now, if I'm just substituting in the denominator part, it will be higher value compared to the numerator, which I have assumed like 0.001. Now, here, this 0.001 divided by, if it is higher value, again from the 0.001, I'll be getting even lesser value. So that will be the new learning rate over here. So by this particular thing, my learning rate will get adopted. All right, my learning rate will get adopted. So, but the major problem with respect to ADA-grad is nothing but by doing so, at one point in time, if this learning rate, if it is equal to 0, because initially it is 0.01. Now later what will happen? This total eta dash t, it will be like 0.0001, then 0.00001. So it will be at one time it will be 0. Then what will happen? New weight is equal to old weight. Weight itself not at all updating. So if the learning rate is not getting adopted, the new weight is equal to old weight. Then how exactly the network will get optimized? So this ADA-grad is getting into the trap of something called as aggressive decay in the learning stage of gradients. So when I'm going for multiple iterations, my ADA-grad is getting into the trap of aggressive decayness. So what is this aggressive decayness? Again, I just mentioned this particular point here. Aggressive decay. So aggressive decay in the learning rate. So there might be a point when the learning rate becomes extremely small. This is because the squared gradients in the denominator keep accumulating, and thus the denominator part keeps on increasing. Due to small learning rates, the model eventually becomes unable to acquire more knowledge, and hence the accuracy of the model is compromised. Model itself will never learn. New weight is equal to old weight. If new weight is equal to old weight, again I have to forward propagate with the same weights. So there is no meaning in doing the same process again and again and again. Able to get my point? So something, if you're for giving your complete attention, you might take it, or else you will feel confused. How many of you understood this? Adaptive learning rate. Supriya, Harsh, Srisha, yes. Harsh, wonderful. Chaitanya, wonderful. Rishikesh, perfect. Narthi, little. Vastush, understood. So. Wonderful, Harsh. Great. In case if you feel this is just a bit complex thing to understand, even I just simplified it. If you're reading this particular thing in your blog and everything, you might find a lot of mathematical equation. Even I simplified it and I'm just delivering it. All right. Even you can watch the same recordings if you're not getting the concepts. But again, you can read anything that you want, which will give you a good understanding about it. Now the next optimizer is nothing but RMS prop. That is, there is another optimizer which I listed it, that is called as ADA delta. ADA delta and RMS prop will work very similar. You can read about it, but let me touch this particular RMS prop. How exactly RMS prop and the next optimizer is nothing but Adam. These are all the very frequently used optimizers. All right, let's get into the math of it. RMS prop. Yep. See this RMS prop mathematical equation. This is what it is. Now RMS prop, it combines, since ADA grad weight update equation is given by new weight is equal to old weight minus eta dou L divided by dou W. So the major problem with respect to ADA grad is nothing but what? Aggressive decay. Why it is aggressive decay? Because this eta dash is having weighted moving average. Sorry, this eta dash is going to have sum of learning rate divided by square root of alpha t. That alpha t is nothing but what? Sum of squared gradient. So when the number of iterations is increasing, that is forward pass and backward pass, number of epochs is increasing, it keeps accumulating its gradient. But if here, instead of accumulating the gradients, I'm replacing this particular part by weighted average, which we have already learned in momentum part. So that exponential weighted moving average, I'm doing it. So this is again given by, see this, there I've just denoted by beta, but here to make some difference, I'm just denoting by gamma. Gamma multiplied by W average T minus 1 plus 1 minus B multiplied by, here if you see this one difference, dou L divided by dou W the whole square. Here also I'm taking all the gradients, but look at the difference. 1 minus gamma. So this gamma, it will be 0.9. So 0.9 weightage you are giving to one timestamp previous. Let's say if you're at the timestamp 10, you are giving 90% weightage to your timestamp 9 and 10% weightage from timestamp 1 to timestamp 8. So there your weights, it won't be carried. It means that kind of aggressive decay, your complete 100% weightage you're not going to give to all the data points. So 90% weightage to one step previous to the current data point, and to all the other data points previously, what do we have? 0.1. So by this particular thing, you're trying to make your network to learn more faster, and the smoother and the zigzags and the vertical movements to reach towards the global minimum point, it will get reduced. Able to understand this point? Just a slight change in mathematical equation with respect to ADA grad and RMS prop. Able to get this? Supriya, Harsh. Just take down. I'm just giving this, made it as a PowerPoint, and I'm just giving this in your dashboard. Slowly go through it. You should be able to get it. Fine. So now let's get into the last part. Adam optimizer, which is the mostly used optimizer. We call it as adaptive momentum estimation. This is what we just most of the times we use only Adam, or we don't use gradient descent. We don't use, but the default optimizer is nothing but RMS prop, but we can change it out. Once we get into the scripting part, I can just show that to you. But the point is nothing but Adam and RMS prop is something we use it often. So Adam is the best optimizer compared to all. That's the reason why we use it. Why? Because see this. Adam combines the strength of momentum optimizer and RMS probe optimizer. It is having a lot of parameters, tweaking parameters. That is alpha we have, beta we have, two beta terms we have. All right. If it is an RMS probe, one beta term you have it. But with respect to Adam, you're having learning rate and you're having two beta terms. See this. Your momentum equation is given by W is equal to what? That is new weight is equal to old weight minus learning rate of VDW. Bias is nothing but B is equal to alpha dot VDW. So now this is nothing but what? Your exponential moving average, right? So here the beta VDW previous and 1 minus B, that is a derivative of this. So this is what we already learned, momentum weight update. Now RMS prob weight optimizer is given by this particular equation. That is new weight is equal to old weight minus alpha divided by DW divided by square root of weighted moving average. And DW is nothing but square root of weighted moving average. This weighted moving average is nothing but again it takes another beta term, right? There I just given by gamma, but here I'm just denoting this by beta. Any parameter you can give it. So beta multiplied by weighted moving average of previous minus 1 minus beta square, DW the whole square it is. That is summation of all your moving average, right? So that's what the point. Now here if you take it, so this is DW and this is DW the whole square. That's the only difference. So here also you're having beta and here also you're having beta. Now here since we are having two beta terms, so here I just denote by 1 and denote by 2. Now Adam weight update equation is given by W is equal to, you're going to combine momentum and RMS prob. New weight is equal to old weight minus learning rate, say this, dot VDW, that is momentum's VDW divided by square root of weighted moving average at time t plus epsilon. Epsilon is just given to avoid, means in case if this weighted moving average, if it is 0, then 1 divided by 0 becomes infinity. So to avoid that particular part, epsilon is nothing but we try to give a value of 10 to the power of minus 8, just to avoid infinity problem. That's it. Now this uppercase VDW, this complete equation, it will be coming in the uppercase. Denominator V, weighted moving average. This particular part, it will be coming in the denominator. So you're having two beta terms, beta 1 in the numerator, beta 2 in the denominator. The same thing applies for B also. So this Adam, since it is having learning rate and two beta terms, the learning process is much more smoother, much more faster compared to all the other optimizers that we have learned so far. Got my point, everyone? Hush, wonderful. Great. Now, whatever I explained as a theory, you can find it here because this is, as I said, this is a long theory. That's what I also already told you. So you can read it. Okay. RMS prob and also Adam optimizer. I've just given some theory here. Faster running time, lower memory requirements, requires less tuning than any other hyperparameters. But again, I've given one more point also. This how to choose between different optimizers. If Adam is the best, then why we have to learn about stochastic gradient descent, normal, NAG, and why did we spend much time over there? So read it. You should be able to understand it. All right. Now let me just walk you through this particular Keras.io. If you look onto it, Keras.io, just get into that and click on Keras.io. If you see this, there is something called as optimizers. Click on it, optimizers. See this, there are different optimizers that you can explore. Stochastic gradient descent. Let me click on this SGD. See this, with respect to this one class, so stochastic gradient descent, here we are having learning rate, momentum, Nesto, name is equal to SGD. So in case if momentum is equal to 0 and Nesto if is equal to false, then it becomes what? Only learning rate, then it becomes what? Momentum 0, Nesto 0. Then it becomes a simple gradient descent equation. All right. In case if you're giving momentum is equal to some value, 0.9 or something, then it becomes stochastic gradient descent with momentum. And that's the reason here I coined this particular term, the exact term, you see. Stochastic gradient descent with momentum. That is the purpose why I just mentioned. See this. point to remember. This is with respect to one class, I can implement four algorithms, four optimizers: stochastic gradient descent, mini batch gradient descent, and the normal gradient descent approach, and the NAG optimizer. Four algorithms we can do this with respect to this one class, SGD. Okay, right. So tomorrow anyway, we will be having this Keras.io as a reference, and we'll be doing it. And let me scroll down, see this RMS prop. Let me click on RMS prop, learning rate, momentum you have, all right. And that row, that kind of row we have given 0.9. Momentum here it is 0. There is no momentum, epsilon. We got it here, all right. RMS prop, right, optimizes. Let me click on, scroll down. And Adam optimizer, let me click on it. Learning rate 0.001 fixed, beta term. So two beta terms is fixed here, 0.9 for beta 1 and 0.999 for the second beta. And we can change it if you want, we can also change it. Epsilon is nothing but what? 10 to the power of minus 8. That's what the point here. All right, optimizes. And see this, there is another ADA delta also you have. See this row. As I said before, your RMS prop and ADA delta will be very similar. See this, only thing is here we're having 0.95, there you're having 0.90, very similar. With respect to ADA delta and RMS prop I'm speaking about. And then ADA grad. Okay, learning rate is 0.01. So see this, initial accumulator value 0.1. And then epsilon value, we got it. So the initial value, we need to set it up. Initial learning rate 0.1. So you can take a read on it. All right, in this particular documentation, just have a read on it and come in. And even I don't want you to understand the scriptings and everything, but just to an Adam optimizer, there will be something beta 1, beta 2, epsilon, an Adam, some differences. They used to release some new optimizers in the market. So we used to have an eye on it. Again, we have to FTRL. What is FTRL? Learning rate power, initial accumulator. Again, we have to study about it. Shrinking, we have to check it out. All right. So these are all the different optimizers which we have. To get best weights and biases, we need optimizers, because when we are backward propagating in time, we forward propagate for the first iteration. We calculate the loss. We have to come back. The loss need to be reduced. So weight updation need to happen. So we have to mention which optimizer we want. Accordingly, the weight optimization is going to happen. All right. And here, if you see, click on loss. Basically, we are having probabilistic loss, regression loss, and also hinge losses. So what are the two types of problem we can have in our machine learning? What we discussed yesterday is nothing but classification, regression problem statement. Only these two kind of problems we can just solve it over here. All right. So if it is a classification problem statement, just click on it. Loss function you have to decide. We are having binary cross entropy. So you can just copy this binary cross entropy and you can just keep it. All right. If it is a multi-class, let me click binary cross entropy and the categorical cross entropy. See this categorical cross entropy when there are two or more label classes. That is for multi-class classification, we have to use this categorical cross entropy. Again, if you scroll down, you can see sparse categorical entropy. Again, for multi-class classification, we can use it. Again, if you scroll down, Poisson class between Y true and Y predicted. So in this way, we are having different, for classification problem statements, we are having this probabilistic losses. If it is a regression, that is when output, if it is continuous, we have to choose this mean squared error, mean absolute error, mean percentage error. Let me click on it, mean absolute percentage error. So this is what we have to give it. That is, if you look on the equation, Y actual minus Y predicted divided by Y actual, absolute value multiplied by 100. Every mathematical equation is also given over here. So this is the task for you all. Just get into this particular loss functions, click on probabilistic losses, regression losses. Just go through it once. It should be better. Okay. Got it, everyone. How many of you felt today's session a bit hectic? Not bit hectic, more hectic? Or is it easy to understand? How did you manage? I said so. Okay. Wonderful, Astosh. It's all about how you're giving your complete attention here. So only then you can take all these topics, or else again you will feel a little bit disturbed, or you won't be able to understand this kind of topics. As I said before, your machine learning is a kind of first standard or second standard topics. Deep learning directly jumping into 12th standard. So our mindset also should be in that particular way. So it demands your complete attention in the session. Yes, Harsh. So only my lecture, maybe it will never help you out, because if you're hearing, even though the lecture seems very much easier or harder, if you feel, you have to do your own study about it. Just try, read out some blogs. First time your mind will never take it. Okay, it will be very hard to take it on this kind of areas. But you already have listened to this lecture. Now do your own exploration, read some blogs, try exploring more. You should be very good in that particular part. Okay. So Nanjam, why you're worrying about certifications? When we get certificate and how much attendance percentage needed to get certification? I'm not sure about it, Nanjam. So regarding certifications, not sure. Maybe I think 80%. I think so. 80 to 85% attendance you have to keep it. When you get certification, I think you can download it from your dashboard itself. If not, try watching the day one's recordings. I'm not sure about it. They have explained already how it would work. Day one recording, the first 10 to 15 minutes, watch it again. You should be good with it. Okay. All right. So today we discussed about different optimizers, different loss functions, and different activation functions. So with that, we are winding up our session now. Let's come back tomorrow by 7 o'clock, and theory is done. And now with whatever the theory we learned, tomorrow we are going to work on one good use case. What is that use case and everything? Tomorrow we'll be learning it. Okay, completely scripting, no more theory. For tomorrow's session, no more theory, only scripting. We will be working on code. Okay, so come prepared tomorrow and try to go through this Keras documentation, what I mentioned. So what is the last day of this program? 25th April. 25th April, it will be the last date. You do have one more week to go. Anjali, please. All right. Fine. Great. So take care, everyone. See you all tomorrow, 7 o'clock. Bye bye. Good night.